Hi, ladies and gentlemen. This is lecture 10, I believe, and we are going to discuss Bayes' formula, Bayes' theorem sometimes is called. What I called last time Bayes' formula was actually not Bayes' formula. That's really called the law of total probability. I will get into that as soon as I pull up the whiteboard. So let me get started. All right, so let me remind you about the last part of last time. So last time we had events E and F, and we wrote the formula P of E is P of F times P condition to F, E condition to F plus P of F complement times P of E condition to F complement. So this is called not Bayes' formula, this is the law of total probability, at least in a special case. We're going to talk about the general case at the end. Okay. So we'll talk about the general case later on. Okay, so let me now switch to what is really Bayes' formula. Now the book kind of doesn't do a great job of this, so I'm going to do it my way. So it's really called Bayes' theorem, first of all. And it goes like this. It's the following observation. Suppose I have two events, A and B. And then we note that if we take the probability, recall that the probability of A given B is the same as the probability of A intersect B over the probability of B. So if we cross multiply this, we see that the probability of A given B times the probability of B is the probability of A intersect B. That's what I called the multiplication law last time. But we can also rewrite this in the following way. It's the same as the probability of B intersect A. And by switching the roles of A and B, we see that this is the probability of B intersect A times the probability of A. Okay, so now I take I can divide everything by the probability of B, and I get the following formula. The probability of A conditional to B is the probability of B conditional to A times the probability of A divided by the probability of B. So this is really Bayes' theorem. The book doesn't write it this way. What the book does is it takes the denominator and uses the law of total probability to rewrite the denominator. So it's also written as the probability of A given B is the probability of B given A times the probability of A over, now we apply the law of total probability, which we have over here, to get the probability of B is given by the probability of A times the probability of B given A plus the probability of A complement times the probability of B complement. So this is what the book does. This is the book's version of the formula. I think it's easier to remember this statement, and then when we need the denominator in the form the book writes it, we use the law of total probability. Let me point out why this can be a useful formula. So A, if we take the first box and we think of A is often called, the event A is often called a prior. So it's called a prior. And the reason for that is usually you know something about A to begin with, prior knowledge. And you usually know less about the so you know something about the probability of A, and you often have information, but not complete information about the probability of B. So B is sort of called the hypothesis. We'll see how this works in practice. And you often also know the probability of B given A. So you know the terms on the right-hand side, in other words, to a certain extent. And from that, you can get information about the term on the left-hand side. You'll see what I mean when we do our first application, which is now. Okay, so here's a problem I found on the internet. In Wayne County, 51% of the adults are males. 49% are females. One adult is randomly selected for a survey involving dietary choices. It's later learned that the selected survey subject was smoking a cigar. Also, 9.5% of males smoke cigars, whereas 1.7% of females smoke cigars. Use this additional information to find the probability that the selected subject is male. So we are going to try to solve this using Bayes' theorem. So in order to do that, we have to figure out what the events are. There are two events here. The first event is the event of being a male. And the second event will be that of being a cigar smoker. Okay, so we have to parse the question. Okay, so first of all, what is the complementary event to being a male? That's being not a male. At some point in time, that would have meant being a female, but no longer. And the complementary event to being a cigar smoker is a non-cigar smoker. Okay. So first of all, we want to figure out some of the probabilities here. What are we asking for? What is the problem asking for? It's asking to find the probability that that a cigar smoker is male, right? Okay, because selected subject is a cigar smoker. So we want to find the probability of being male given there's a cigar smoker. Okay, that's what the problem is asking for. Okay, so we can compute that by computing some other probabilities. So first of all, let me state what the various things are. So what's the probability of being male? That's 0.51 according to what's given to us in the information, and 0.49 is the complementary probability of being non-male or female. Then we also have the probability of being given a male, whether that male is a cigar smoker. This is something that is easy to gather this information because you can just go to a population of males in Wayne County and then randomly ask males whether they smoke cigars. And so we know that 9.5% based on survey data, we know that it's 9.5%, so that's 0.095, this probability. Okay, there's another thing we should probably figure out, which is the probability of, you'll see why, the probability of being female, given a female, whether that female, the probability of a female being a cigar smoker. Well, that's given to us also. It's 1.7%, so that's 0.017. So now, what does Bayes tell us? Bayes tells us that the probability of a cigar smoker being male is the same as the probability of, well, it's given by the product, the probability of a male being a cigar smoker, given a male, whether that is a cigar smoker, times the probability of being male divided by the probability of, uh, being a cigar smoker. Okay, so now I want to point out that the prior is being male, and the evidence or the hypothesis. So is the probability of being a cigar smoker in all of this. The right-hand side are things we can measure, right, by doing surveys. It's the left-hand side, the probability given a cigar smoker, whether that cigar smoker is male or not. That's not something that's easy to measure directly from a survey, but Bayes' formula will enable you to compute that. So we have most of the information except what is P of C. P of C is using the law of total probability. It's the probability of C given M times the probability of M plus the probability of C given M complement times the probability of M complement. And that's going to be given by 0.51 times 0.095 plus 0.49. Oops, I'm not doing this right. Hold on, let me erase. Okay, so that would be point. So on second thought, and I was interrupted by a phone call, I'm not, let me compute this elsewhere. Okay, so what do we got? So the probability of a cigar smoker being male, I'm going to compute this over here, is given by probability of a male being a cigar smoker, which is 0.095, times the probability of being a male, which is 0.51, divided by, now we use the law of total probability to compute the probability of being a cigar smoker. So it's 0.095 times 0.51 plus 0.017 times probability of being female, which is 0.49. And what do you get? If you did this correctly, you get 0.853. So about 85% of the time, you could expect probabilistically that a cigar smoker will be male. So that is the kind of Bayes theorem calculation. So let's move on to another problem. So this problem I took out of a magazine called Scientific American. It goes like this. A patient goes to see a doctor in a county consisting of 10,000 people. The doctor performs a test with 99% reliability. That is 99% of the people who are sick test positive and 99% of the healthy people test negative. The doctor knows that only 1% of the people in the county are sick. Now the question is, if the patient tests positive, what are the chances that the patient is sick? Okay, so let's get started with that. All right, so I'm going to first of all write down what the two events will be named. So this D will be the event of actually being sick, the patient's sick, and T is the test is positive. Okay, and now we are testing, we have 10,000 people in the entire county, right? So we have to use that fact. Okay, so now the first fact is that the probability of being sick is easy to compute because we know that what? We know that 100 people, 1% of the people are counted, are sick, so it's 1% of 10,000. So in other words, we know that 100 people in 10,000 are sick. And we also know the probability of testing positive. We, uh, we know that, and I'll show you what that is in a moment. It's actually convenient to actually put the data on a table. So let me pull up a table. Okay, so what do we know? I've just drawn a table, and I'm going to input the information into a table. So the table has on one side the T and the T complement, on the other, that's in the rows, and then you have D and D complement in the columns, and then you have totals. Okay, so now what do we know from the 10,000 people in this county? We know that out of 100 people, 100 people are sick, because that's 1% out of 10,000, and we know that the remainder are not sick, 9,900. So that we know, okay? We also know that the probability of testing positive is, we can compute that. How do we do that? Well, we know, first of all, that uh, that we know that 99% of the people who are sick, that's D, test positive. So 99% of 100 is 99 people who are sick will test positive. So you can fill in that element in the table as 99. Likewise, we also know that 99% of the healthy people, that's not sick, will also test negative. Now, what is 99% of the healthy people? Well, the healthy people are, there are 9,900 of them, so you have to figure out what 99% of 9,900 is. So what is 0.99 times times 9,900? That should give you 9,801. So we can put a 9,801 here. That comes from the second sentence of the question. Okay, we also know, because the column entries under D have to add up to 100, that the number of people who are sick, which test negative, that's a false negative, is 1, and likewise, we know the remaining people, 99 people who are not sick, test positive. Okay, and then we can add up the totals in the rows. We get 198 and we get 9,800. Okay, so we filled in all the entries in the table. So now we also know what the probability of T is. The probability of T is given by 198 divided by 10,000, because the number of T's is 198. Okay, which is 0.0198. Okay, so now what is the question really asking? The question is really asking, if a patient tests positive, what's the probability that the patient is sick? So we want to know, and that's actually a very important question. So what is the probability if the patient tests positive that the patient is sick? So now we're going to use Bayes' formula. Bayes' formula says that that's the probability of T D times the probability of D divided by the probability of T. Okay, and now what do we get? So what's the probability of T given D? So we have to figure that out. Well, uh, that is, that's not hard because that's actually given to us. It says that 99% of all people, yes. So what is P of T given D? Well, we can actually compute the probability of T given D just directly from the table because that's the same as the probability of T D intersect D over the probability of D. And the probability of DT, well, it's 99 out of 100 people. And the probability of D of being sick is given by, no, I'm not going to do it that way. So what is the probability of T given D? That means if you're sick, what is the probability that you test positive? Well, that's given to us in the problem itself. That is 99% of the people who are sick test positive. So if you're sick, you test positive 99% of the time, so that's 0.99. So therefore, we have all the information to plug in. 0.99 times P of D, we have P of D as 0.1, over the probability of T, which is 0.0198. And that is 0.5. So 50% of the time, if you test positive, then you have the disease. So the test only gives you about, is only accurate up to about 50% of the time. That's what this is telling you. Okay, so those are two problems for today. We'll be doing more of these problems next time in the next lecture. What I'd like to do next is to generalize Bayes' theorem to a more than two events, more than one event. Okay, so let me do that now. So first of all, we have the generalized law of total probability, which I'm going to explain now. Suppose I have events F1 through Fn, and I want them to be mutually exclusive, which means that Fi intersect Fj is empty if I is not j. And I want them to be exhaustive. So that means that if I take the whole sample space is the union F1 union F2 all the way up to Fn. It exhausts the whole sample space. Okay, so under these conditions, suppose I'm given, so that's given a bunch of F's, and then we're given an event E. And the first statement that I want to make, and this is the generalized law of total probability, is that the probability of E is given by a sum. It's the probability of E given F1 times the probability of F1 plus the probability of E given F2 times the probability of F2 and so on, dot, 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 all the way to the end, which is the sum, I goes from 1 to n, of probability E Fi times the probability of Fi. So that is the generalized law of total probability. Okay, so I'm then now going to generalize Bayes' theorem as follows. So if we're in the same situation, the statement is if you want to compute the probability of Fj given E, you can compute it by taking the probability, so J is one of the indices, the probability of E given Fj times the probability of Fj, and it looks just like the usual Bayes theorem, except there are more terms. It's the sum that appears in the generalized law of total probability. So that would be the summation I goes from 1 to n, the probability of E conditional to Fi times the probability of Fi. So this is actually useful, believe it or not, and we're going to do examples next time which use this formula. So I'm going to stop here, and this will be the last lecture of week 3 in the course.